Good day, everybody. Justin Miller, Upstart College Physics. What do we got going on? We got more projectile motion and some other things to explore regarding them. So there's a couple things that we want to do. Let's just start off, right? We know the equations of motion for a projectile, and we're considering, again, no air resistance, so only the gravitational acceleration is pertinent to the system. And the question becomes, hey, what is the shape of that trajectory? It goes up and it comes down and it follows a certain path, right? Is there some mathematical representation of that path? Bad three-eyed juggle right now. Anyways, is there? Sure there is. Sure there is. Let's figure out what that is. I'll juggle later at the end. Okay, so we want to look at the path of a projectile. Is there again some mathematical representation of it? And some of you probably know or have heard that, hey, it's parabolic, it traces out a parabola. Let's see if that's true. If it does, we should be able to show it, right? Is it parabolic? Well, we could draw it out, or we could throw something and say, oh yeah, it kind of looks like a parabola. Let's show it, right? So we've got ourselves a couple expressions, some fundamental time-dependent expressions for a projectile. We've got ourselves that delta y is equal to negative 1/2 g t squared plus vyi times t. Displacement in the y direction as a function of time. We've also got ourselves that delta x is vx initial times t. Distance equals rate times time, or displacement in the x direction is velocity times time. All right, so what we want to know is what's the correlation between the displacements itself. The displacement's really related back to its position based upon the difference in its location with respect to its initial position. So let us say, just for argument's sake, this is the easiest way to show this, that y initial is equal to x initial is equal to 0. Let us just say that, because then we can change these from displacements to actual positions. It just looks a little bit cleaner. So that delta x is equal to x final, and delta y is equal to y final. We're just kind of taking out some constant that's arbitrary anyway. So we've got this going on. We can change both of these expressions to, well, this one now becomes y is equal to negative 1/2 g t squared plus vyi times t, and this one becomes x is equal to vxi times t. T equals 0, we're at 0 meter mark. T equals 0 for this, we're at the 0 meter mark, then it evolves from there. All right, so what can we do? How does that show that it's parabolic? It doesn't yet, but let us try to get rid of time. We really want a function that describes its position in the y direction with respect to its position in the x direction, right? So we decide on something. What are we going to do? We need to eliminate time between these two and have some correlation between, well, the y position and the x position. Y of x, if you will. So let us take this and solve it for time here. Well, that's pretty easy because we just divide both sides by vx initial, and we've got time is x divided by vx initial. Now what we're going to do with this is we're going to take this and substitute it in there for time and there for time. Sub. So we're going to eliminate time in favor of the position x and something that's constant, the initial velocity in the x direction. So let us rewrite this now. I'm going to change colors here. So I'm going to take this now with that substitution taking place and write this as y is equal to negative 1/2 g times t squared. Well, t is this. So we've got x divided by vx initial quantity squared. We stick that in for t. Good. And then we've got a plus Vx initial times t, where t is x divided by Vx initial. All right, let us just clean this up a little bit. And I'm going to take this Vx initial squared out and stick it over here. Likewise, I'm going to take this one out and stick it over here. Sorry, that's not a Vx initial, it's a Vy initial. Vy initial. And that's pretty much that. So, you can clean this up and I can write this as then y is equal to -1 divided by 2g times Vx initial squared multiplied by x squared, good, plus Vy initial divided by Vx initial, Vy initial divided by Vx initial times x. This is the y position as a function of the x position. And look at this. We have something that is of the form y is equal to ax squared plus bx plus c, or in this case, c is equal to 0. What's this a generalized equation of? That's right, it's a parabola, where a is equal to -1 over 2g Vx initial squared, that's just some constant, and this should be a capital B, sorry about that, and b is equal to Vy initial divided by Vx initial. We already said c is 0, that's because we're starting at 0, 0. The negative sign here for a gives us a parabola that is whoosh, like that. That's exactly what we get for projectile motion, right? Move something up, it's got this nice curvature, it's better with the ball. All right, so that's pretty much this. General equation of a parabola. So mathematically, there we go. Fantastic. Parabolic. Could actually go a step further with this, believe it or not. Yeah, let's just do it because it's fun, it's insightful, and it comes in handy for some other things. So, how about we start expanding something out? How about we start expanding out Vx initial and Vy initial and see if we can get something that's correlated with the actual initial velocity and the angle of the initial velocity. So that just shows that it's parabolic, but we can get something that even looks a little bit more crazy. We know that Vy initial is equal to the magnitude of V initial multiplied by the sine of theta V initial. And we know that Vx initial is equal to the magnitude of V initial times the cosine of a theta V initial. What happens if we put those into that expression here? Here for Vx, and there for Vy, and for Vx. So, we can write this now as y is equal to -1 divided by the quantity of 2g times V, magnitude of V initial, times the cosine of theta V initial squared. Ooh, that whole quantity squared there. And that's going to be multiplied by x squared. All right. And then what? Well, we've also got ourselves a plus Vy initial. Well, Vy initial is the magnitude of V initial times the sine of theta V initial. And that's divided by Vx initial, which is Vi initial. V initial, sorry, cosine of theta V initial, and that is then multiplied by x. We may say, ooh, she just made things look kind of a lot uglier all of a sudden. But there's some nice things with this. One thing is that this V initial divided by V initial, that goes away. This is just squared, this is squared, and we've also got that sine divided by cosine. Trig ID, right? The sine of theta divided by the cosine of that same theta is the tangent of theta. Yes, so we can rewrite this all and say that y is equal to -1 divided by 2g v initial squared, because again it's this whole term squared, so v initial squared times the cosine squared of theta v initial multiplied by x quantity squared divided by, again, those two cancel each other out, sine divided by cosines, tangent, so we've got plus the tangent of theta v initial multiplied by x. This ends up being a handy expression for certain applications. Calculus-based course, we'll use this. For the one that's not, don't worry about this too much. It's just kind of cool to see. But what one can do is start thinking about the variation of initial angles and the consequence of that. Or, we could solve this all out for V initial. If we want something to have a certain Y and X position at a certain, well, given a certain initial angle for the velocity, there's a certain speed at which we can do something. I take a ball and I say, you know what? I want this ball to strike right here. When I throw it from right here at a certain angle, like 45 degrees, how hard do I have to throw it? If I don't throw it hard enough, it doesn't get there. If I throw it too hard, it hits up above it. If I throw it just right, it hits the spot that I want it to. There's a certain speed for a given angle that produces a certain displacement in the x and y directions. So it comes in handy for solving that, and yeah, that's good. All right, so show that it's parabolic. We've got another expression that comes in handy once in a while. And one last thing that we want to do. And that thing that I want to do is say what angle of projection, initial angle of the velocity, will maximize the range of the projectile. So, let us take a look at that. For a given initial speed, what initial angle will maximize the maximum displacement in the x direction. So, the initial answer is to this, it depends. Oh shoot, that's not a good answer, huh? What does it depend on? Well, it doesn't depend on the speed, because we're saying given an initial speed, what angle maximizes the range, the maximum displacement. What it ends up depending on is what is the overall displacement, the y direction this object is going to undergo. So what we want to look at is a particular case. Let us assume now that the object returns to the elevation from which it began. So that is going to be our contingency here. And now I'd say there is a particular angle, given that. There's a particular angle for a particular displacement in the y direction. So I can take say some ground level or some initial elevation from which we're going to have a projectile. We start with it here, and what do? We throw it, we kick it, we launch it, whatever. But it's going to come back to the same elevation. So we can do it with the same speed, but at different angles, and see what we get. I could throw this ball, well, if I throw it straight up, you think about how far away it comes, it's not that far. As I throw it more and more in the X direction, well, it kind of goes farther and farther until, well, I have too much in the X direction. There's a certain angle, ultimately, is what it comes down to. So, just for instance, I could throw it up high where it goes whoosh. I could throw it like this. Where it goes quite a bit farther, right? Or I could throw it at a very, very shallow angle. Let's do some purple here. That was a pretty bad one. Oh my gosh. Try that again. All with the same initial velocity, but I get different outcomes here. One of these angles in between 0 degrees and 90 degrees maximizes the range. And some of you may know what it is, or heard that that's 45 degrees. You want something to go the furthest, throw it at 45 degrees. Well, number one, that assumes that it comes back to the elevation from which it began. And number two, we want to show it, right? You've heard it. How do people know that, right? Why do people say that? Well, because you can show it mathematically, that's why. So let's do that. So what do we have? Well, we've got this. We've got that delta x is equal to Vx initial times t. That's good. What else do we have? Well, we've got delta y is equal to Vx initial times t. Excuse me, Vx initial times t. We've got ourselves the other equations for the y direction. We've got delta y is equal to negative 1/2 g t squared plus vyi times t. We've got ourselves that vy final is equal to negative gt plus vy initial. And we've got ourselves that vy final squared is equal to vy initial squared minus 2g delta y. So let's think about some things that we know regarding this. It comes from this initial statement here. Our initial assumption that we're going to work under is that this object comes back to the same elevation that it began. This here says something. Delta y is equal to 0. Fantastic. Delta y is equal to 0, so what else do we have going for us? Well, look at this. If delta y is equal to 0 overall, we have that the final velocity squared is equal to the initial velocity squared. So let's try to use this. With delta y being equal to 0, we've got that vy final is, well, initially it was going up, right? And then finally it's coming back down in the y direction. So we have vy final is equal to negative vy initial. Take the square root of both sides, plus or minus, got to pick the minus. So we've got this. What can we do with that? Well, what happens if we stick that in here? Let's see. That relation here. If I go ahead and say that vy final is actually equal to negative vy initial. So now this expression here becomes negative vy initial is equal to negative gt plus vy initial. We can start grouping some things, right? What happens if I subtract this from both sides? Well, I'll have negative vy initial minus vy initial. So let's do that. Minus vy initial minus vy initial is equal to negative gt. What happens if I go ahead and solve that for time? Well, this is negative 2 vy initial, and that's going to be divided by negative g. So I get from this that t is equal to 2 vy initial divided by g. So there's the total time that the object's in the air for if it comes back down to the same elevation from which it began. So now we've got this. Well, with that, we can do something else because we got an expression regarding displacement in the x direction as a function of time. Here's the total time that a projectile is in the air. It's based upon what is its component in the y direction. So let's go ahead and take this. Now sub this into there. What do we do with that? I'm going to take this now and rewrite it. We've got delta x is going to be equal to Vx initial multiplied by 2 Vy initial, 2 Vy initial divided by g. All right, well, what does that really give us? It just gives us the relation between delta x and the x and y components of the initial velocity. But the x and y components of the initial velocity are related back to the initial velocity as a magnitude and a direction, right? So let me go ahead and take this down. He's gonna need it. Erase this. We're almost there. Oh, yes. I'll rewrite it. So we know this. We know that Vx initial is equal to the magnitude of V initial times the cosine of theta V initial, and Vy initial is equal to the magnitude of V initial times the sine of theta V initial. So what can we do with that? We can take those, put that in for this and this, Vx initial and Vy initial. So now this becomes delta x is equal to the magnitude of V initial times the cosine of a theta V initial multiplied by 2 times the magnitude of V initial times the sine of theta V initial, quantity divided by g. Now we've got the displacement in the x direction. This is the total displacement, right? Total displacement by the time it reaches the ground in the x direction, written in terms of the angle of projection and the initial speed here. Well, what can we do with this? Let's kind of group some constants together, because what we're really looking for is what angle maximizes the displacement in the x direction. So let us kind of get everything else to the other side. I've got a 2, I've got a g, I've got a v initial there and a v initial there. Everything's being multiplied and divided by g. So we're going to rewrite this as delta x is equal to, I'm going to write it as v initial squared divided by g, v initial squared divided by g. I'm dropping the magnitude sign, doesn't really matter, multiplied by 2 sine of theta v initial cosine of theta v initial. Everything's there. I've rearranged things a little bit, but there's a reason for that. Because this here, that's another trig identity, right? 2 sine of theta cosine theta. What is that? This is equal to the sine of 2 theta v initial. Trig ID. So now we rewrite this. We rewrite this as delta x. The total displacement in the x direction is v initial squared divided by g times the sine of 2 theta v initial. This is some constant that just depends on how fast you initially throw it. We're keeping that at some rate. What we want to look is the variance of the overall outcome of delta x relative to the angle of projection here. The sine of anything just alternates between 1 and -1, right? The sine function just goes 1 and -1, 1 and -1, 1 and -1. 1, -1. This is just the sine of theta in general. Well, we make it 2 theta, it doesn't matter. It still just alternates between 1 and -1. The greatest that this can be, greatest that the sine of 2 theta can be is 1. It's the greatest that it can be. Otherwise, it's something less than 1, and something less than 1 times this is going to be smaller than if sine of 2 theta is actually equal to 1. So really the greatest that delta x can be is V initial squared divided by G. So delta x max is equal to VI initial squared divided by G. So the question becomes, what angle will make that be equal to 1? Theta sub V initial equals what? Such that sine of 2 theta V initial is equal to 1. There's the question. We answer that, and we've got ourselves. Well, we know that the sine of 90 degrees is equal to 1, right? There we go. So 2 theta V initial must be equal then to 90 degrees. And if that's the case, then theta V initial must be equal to, that's it, 45 degrees. So that is the angle of projection that maximizes the displacement in the x direction if the object's returning to the same elevation from which it began. If it's returning to a lower elevation, well, this ends up being incorrect. As the elevation drops below the initial elevation, this angle actually gets smaller and smaller. But it's a good approximation if you're throwing something decently hard and you're only like a meter or so off the ground. It's negligible. But there you go. Pretty cool to see. There it is. All right, that's it. Have a good one. Be well. I forgot that I said that I juggle. Some projectiles, yay! That's it. All right, there you go.